All right, ladies and gentlemen, today, all right, we are looking at infinite sequences and series, or our first look at them. We're also going to look at them tomorrow as well. And so far we found sums of finite lists, right, where we knew the nth term. But we are going to consider what happens if I have a sequence that goes on forever. So, I mean, sequences that I guess you probably already know that do that are like this. This is a arithmetic sequence that goes on forever, right? The natural numbers. However, that one is not a sequence that we would be able to find the sum of. And also, we won't be, for any of these infinite sequences, we won't be finding the infinite term. Well, we'll be finding a formula for any given term, but we won't have like a term for the infinite one. Because, right, that just wouldn't make sense. It's always getting bigger.
A sub infinity.
Yeah, A sub infinity. But we will find S sub infinity, the sum of an infinite list. Now, what do you suspect the sum of this list would be? 1 plus 2 plus 3 plus 4. That's just going to go, like, that's going to add up to infinity, right? If I have infinitely many numbers there and all of those numbers are getting bigger, those numbers are going to add up to infinity, right? How about, let's consider a geometric. What if I've got 2, 4, 8? What do you suspect about that one?
Infinity.
That would also add up to infinity. Now, it turns out the only kind of geometric sequence that could add to a specific number if I have infinitely many terms would be what kind? Do you have a comment, question, observation?
It would be decimal. It would be a decreasing.
All right, so yeah, it would have to be a geometric with r being less than 1. So let's consider that. So what if I had 8, and then 4, and then 2, and then 1, and then a half, and then a quarter, and then an eighth. And notice that each term is getting smaller. Let's see, what am I doing? 16th, right? Yeah, 1/32. So if I add up infinitely many of those, that's actually going to equal a specific number. It's going to be kind of weird to think about.
It's going to be 16.
16?
Yep.
Why do you suspect that? 8 plus 4 is 12,
13,
14, 15. And you think that all of these add up to...
Because there'll be 1/2 and 3/4 and 7/8 and 15 16ths and 31 32nds and 63 64ths and 9 27 28.
Yeah. So that might be. So that's eventually where we're going to lead. But before we even get there, we're going to have to talk about limits, where we're going to consider the following. Let's see, what color am I? I'm orange. So the limit as n approaches infinity of 1 over n. So let's see. So this kind of like, did we do sigma yet? No. Sigma, well, yeah, sigma sub x bar. But did we do like the Greek capital letter S where we were finding sums? I'm trying to remember. I think I did that a little bit with, yeah, it looks like a weird E. All right. Yeah, so the same sort of thing. So n is going to be values like 1, and then 2, and then 3, and then 4, all the way up to infinity here. And so what I've got here is I'm saying what happens to this number as n approaches infinity. So I've got a finite number divided by a number that's big, really, really big. All right. So let's...
Really, really small.
Yeah, that number is going to be really, really small. Right? So it'd be like divide a pizza into 8 slices. All right? The size of those slices are decent. Right? Divide a pizza into 100 slices. Those slices are a little bit smaller. Right? Into like 1,000 slices. Like each person's slice is just going to be getting like really tiny. 1,000,000 slices, 1 billion, a Google slices. right? Infinitely many slices. As like
Google.
as the number of slices goes to infinity, right? The people that I share it with will be less appreciative for the gift.
Right, a Google slices would be impossible since Google is larger than the number of electrons, protons, and neutrons in the entire universe.
Yes.
Is Google actually?
Yeah.
One
Yep.
followed by 100 zeros.
So that's
And a verb.
a
Now officially a verb.
verb.
I'm going to Google it.
Oh, yes. Yeah, okay. Yeah. Although, Google, that's the number Google, which I even have started spelling it with an L-E at the end. But anyways, so what do you suspect this is approaching? All right, that's what a limit means. It's saying consider the word limit in our everyday life. If I have a speed limit, I can drive up to that number, right?
Well, you should.
Or I should, right? Right. If I have limits on, right, my bank account, I can spend as much or as much money as I can until I approach zero, right? That's the limit maybe on my spending, right? So what I'm asking here is, what is the limit of this? What is this approaching as n goes to infinity? So what do you suspect?
Zero.
Yeah, so that is approaching zero. And it turns out that any series, all right, where my terms as n goes to infinity, if those terms approach zero as n goes to infinity, that means I can then find the sum of that infinite list. Okay? So, so regarding this one, I think I've done this before, where, right, if I told you guys could leave class early today, however, every minute you can only cut your distance to the door in half,
Never reached.
right, you would never reach the door, right? Right, so you'd start like 16 feet away, and then a minute later you're 8 feet away, and then a minute later you're 4 feet, 2 feet, 1 feet, half a foot, quarter of a foot, 8th, 16th, 32nd, 64th, and you just keep getting closer and closer, and you'd never get there. But if I asked you what your limit was as the time approached infinity, you would say that you were approaching the door, right? Like everyone would agree with that. Like that's where you were going. You're never going to get there, right? That's where you're going. Graphically speaking, we would consider this somewhat asymptotic, right? Where we've seen asymptotes before, where it approaches a line or a curve and gets infinitely close to it, but never gets there. In some futile attempt to achieve what it desired, it fails indefinitely, sadly. So that's the idea of a limit. And then it turns out that it's also true that for the limit as n approaches infinity of 1 over n to the r, okay, it turns out that this is also equal to 0 as long as r, this r, all right, this is kind of different. Well, they'll actually say is greater than 0. Oddly enough, because even if r is a fraction, right? So even if I have like the square root of n, right? So if I have like 1 over the square root of a million, or right, whatever those numbers are, even the square root of those numbers, like square rooting infinity, is still going to be infinity eventually. Like it's not going to be able to really slow it down. So when I consider infinity and things that are approaching infinity, I think of like, right, if I have like...
But if it was negative, then it would flip. And then it would be
right
to the positive one.
And then that one would trail off to positive infinity instead of 0.
Yeah, but how does actually apply the problem?
Oh, we'll get there. We'll get there. We'll prove it first, and then tomorrow I think we'll actually get to the formula. So, and what I want to point out is, right, infinity is, I view it as like a freight train, right, coming down the tracks, right? And if I did the limit as n approaches infinity of 1 over n minus 1, what do you think that's going to be? This denominator, what is the denominator? Well, first of all, what is n approaching?
N is approaching 0.
N
is approaching infinity.
is approaching infinity. What is n minus 1 approaching?
Infinity minus 1.
Infinity minus 1, right?
Still infinity.
Which is still going to be getting to infinity. Like, subtracting 1, it's like having that train coming down, barreling at you, and then, like, you've got, like, a little pea shooter, and, like, you hit it with, like, your little pea. It's not going to stop the
It's
train.
gonna have an impact, but it's not
Yeah, it's negligible, right? And as a matter of fact, what if I did n minus 100?
Still would be
Right, but still, I'm not putting a dent in infinity. And no matter how big this number is, as long as this number is finite, I'm still approaching infinity.
still.
I just maybe set it back for a little bit, but it's still going off to infinity. So it doesn't even put a dent in it. So I just want to point out that even that would be 0. Okay? Right, so n
Unless it was n
is
minus
approaching infinity. N minus some big number, no matter how big it is, as long as that number is finite, n minus that number is still going to be infinity, and then
What if it
1
was n
divided
minus
by-
infinity?
well,
Then it would start to approach 1.
well, let's consider that. Limit as n goes to infinity of 1 over n minus n. I could
No, n
simplify
minus
that.
infinity.
Well,
N minus n would just be 0.
yeah, that's what I'm saying. And actually, that is an interesting question. Limit, that'd be 1 over n minus n is 0, yeah. Uh-oh. I
Yeah,
think-
0.
I think that would just be approaching undefined, right?
And XL.
So what do you do? Just earn layers along the way?
No,
Yeah,
if you
that
had
one
n
would
minus
just be-
infinity, it would start at 0 and it would approach 1.
Hmm.
If it was n minus infinity, you'd start at
I don't think
0.
you can use infinity in that fashion. You can approach infinity, but you can't actually just straight out have infinity.
Why not?
So,
You can have n minus n. You can have n minus anything else.
so with that in mind, let's do this example. No, nonsense.
I think Kate's bringing it.
Estimate the limit. All right, so let's say I have this pattern, okay? So what if I have 9/5 as my first term, then I've got 16/4 as my next term, and then I've got 65/27 as my next term, and ... and then I've got, it turns out this is what my nth term formula looks like, 7n squared plus 2 all over 2n squared plus 3n. And that's the nth term, but it keeps going forever after that. Okay?
Did you just make that up?
No. But I mean, we could have, I suppose. But no. Now,
16/4 is 4.
right, but sometimes in the interest of maintaining a pattern, it sometimes makes sense not to reduce that, just so the pattern is more observable to us.
That's strange because it goes from about 2 to 4 to less than 4.
Yeah. Well, I mean, this is a polynomial function over a polynomial function, so it could kind of have some peaks and valleys in it. But then maybe for the extreme behavior, it settles down somewhere. So if I want to estimate the limit, maybe we could do this on a calculator. Let's see, I think I've got this up and running. So let's actually,
Wow, that's got a shadow.
it does?
Yeah. Move it.
I'm not
That
sure.
window has a shadow on the window behind it.
Oh, like
Look
there,
near the edge.
over, yeah, down at the bottom there. Yeah, that's just a Mac fancy thing that they're doing. So let's see. So let's enter my equation as, let's see, I'll have to do parentheses, then 7x squared, and I'm just doing this for sake of convenience. Plus 2, close parentheses, divide by 2x squared plus 3n, or 3x in this case, whichever. All right, so I've entered that in, right? And I can graph that if I want. And yeah, as we said, there's a little bit of weird polynomial jumps and jumps and jives. But this we're claiming is going to be asymptotic, that this is going to be approaching some number as n trails off to infinity. So let's actually do a second calc, and I'm going to calculate some values here. So let's calculate what happens when n is, I don't know, 50. That's a big number. Uh-oh. What doesn't it like? It doesn't like 50? Really?
Oh, it's your X max. The problem is you don't have a big enough mass.
Let's see. So actually, yeah, there's some vertical asymptotes there as well. Well, let me do this. Let me start at 0, and let's count by hundreds. Let's see if this works, hopefully. And we'll go to the table. Okay. So at 100, it's at 3.45. At 200, it's at 3.47. Let's see. Is this actually... man, this isn't even in float. What is going on here?
You had it set.
Okay, so 3.448, 3.74, 3.826, right? And, right, it's getting closer and closer to... Yeah, so this isn't going off to infinity. It seems like it's slowing down. Let me try plugging in a larger value. Yeah, it might be. It might be. So let's enter 2,000 maybe. Count by 2,000s.
Eventually, it will hit a spot where it will round up to 3.5.
Based off of the calculator's limits. So as I plug in really high numbers, it appears as though it is approaching. Oh, what was that? Oh, yep. Yeah, so that's the calculator's limitations of the number of digits that it can store, right? Yeah, I hit down. Let's see. So I just want to point out that when I plug in values here, it appears as though this is approaching. So I could say the limit as n approaches infinity of 7n squared, let's see, that's not a 7, 7n squared plus 2 all over 2n squared plus 3n. It appears that this is equal to 3.5. Equal. It's not.
That just means the limit. That's the
Right.
limit. It's not what that sequence is.
So that's how you could approximate a limit by just trying, like, I don't know, let me plug in some big numbers and see where they're approaching, right? And we've done that with end behavior for asymptotes before, where we've realized, like, oh, this is approaching 1 on the x-axis, right? Things like that,
7 divided by 2.
as x goes to infinity. What?
7 divided by 2 is 3.5.
You might have noticed something that is true. So let me actually show you guys. So we've got actually a whole bunch of properties of limits here. I'm not going to have you write these down, but most of these make sense. So I'm just going to verbally confirm these. We'll look at these together. What? It snapshotted that as well. That's funny. That's funny.
Nice.
Let's see. Nice. Thanks a lot, book. Computer. Blah, 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 blah. Here we go. All right, so let's paste this. So we're just going to look at some of these. I guess these are kind of properties of limits. Okay, so it turns out, okay, limit of a sum. So let's look at this and see if this makes sense. So it says the limit of some function plus some other function is equal to the limit, or the sum of both of those functions' limits. Right? So imagine if function A is approaching 0, function B is approaching 1, the limit as of, right, A plus B would just be 0 plus 1 or 1. Right? So that seems like that would be believable. Turns out the difference is true as well, right? So I can break it up into just two separate limits. All right? Limit of a product, I can break up into the product of two limits. All right? Limit of a quotient, I can break up into the quotient of two limits, and then they have one stipulation. And why is that?
Because you can't divide by 0.
Because I can't divide by 0. Wah, wah, wah. Right? And then the limit of a constant. What is the limit as n approaches infinity of 2?
infinity of 2.
2. Because there's nothing changing about it. It's just 2 all the time. Right? Like n had no effect on it. So it's saying that the limit of a constant is that constant.
So if it's not an adaptive.
Yeah. Yeah. So so let me show you some cool tricks. So here we go. What was it? Here, let me snapshot this right here. And we're actually going to do this now algebraically instead of estimating. We're going to find this exact.
Okay.
I guess I don't need to zoom that up. So let me show you this trick. So I'm going to divide each term by n to its largest degree. Oh, degree starts with a G. Nope. Starts with a D.
Hang on.
Gedry. Yes.
Hang on. Okay, so divide.
So that will be the general strategy. And then I'll be able to use all of those limit properties to kind of break it apart into all separate limits, and we'll see what happens here.
Divide each term by n
And just like with logarithms, you'll wish you didn't have to write limit as n approaches infinity as much as we'll end up writing it. So I'm sorry. I apologize. And by the way, limits don't just work with things that approach infinity. We'll also at some point deal with limits where n approaches 1 or 0, right? So that negative infinity even, right? So different things like that. So what I'm saying is, let's see. So looking at all of the n's here, what is n's largest degree?
N squared.
Right, squared. So I'm going to write this as 7n squared divided by n squared plus 2 divided by n squared all over 2n squared divided by n squared plus 3n.
Oh my god, I can't keep up.
Yeah. I'm pausing here. So I divide every term by n squared. Which is a legal move, right? I can do that. Essentially what I did was I multiplied by 1 over n squared all over 1 over n squared, which is fair game. So what does this simplify to be?
7 plus 2 over n squared.
So those cancel out, so that's 7 plus 2 over n squared.
All over 2 plus 3 over n.
Right, because properties of exponents. Right, these canceled, this canceled with one of those. Right. So, now, I won't necessarily make us write this, but this is going to be the same as the limit of 7 plus the limit of that divided by the limit of 2 plus the limit of that, right? Like, I could use all of those properties we just talked about to separate this into 4 separate limit problems, right? And then I'd add some limits and I'd divide by the sum of some other limits, all right? I could do that, but we won't
Limit
have
of
to.
7 is 7.
Right, so as n goes to infinity, the limit of 7 is 7. What is the limit of this? 2 divided by a really big number.
0.
Is a really small number. As n goes to infinity, n squared also goes to infinity. Dividing 2 by a number that's approaching infinity is 0. All right. What is the limit as n approaches infinity of 2?
2.
2. What is the limit as n approaches infinity of 3 over n? 0. Okay? So, this is the same as 7 halves. No more limit.
Which equals 3.5.
Why? Wait, can you say that again?
What is the limit of 7 as n goes to infinity? It's just 7 all the time.
Because there is no n.
Because, right, it's just constantly 7.
But how would the 2 over n squared and 3 over n?
Well, 2 divided by infinity. Right, think about this. 1 divided by infinity was approaching 0, right? 1 divided by this, even if the r is squared, right, or cubed or to the 7th, this limit is 0.
So as long as they're both approaching the same limit, they can cancel out.
Right, these ones canceled out, and that just became 7. That was algebra there. I didn't take the limit until this very last step.
So are the 3 over n and the 2 over n squared both approaching infinity or both approaching 0?
3 over n is approaching 0, 2 over n squared is approaching 0.
That's why they cancel out.
Yep. Yeah.
Adding 0 to anything is
So let's do another problem here. Last example, I think. So find the limits. This time I'm just going to give us our nth term because I don't... Nope, that's not how you spell limit. Limit as n approaches infinity of, and let's say I had this, 2n to the 4th plus 3n squared minus 1 all over,
That's not a very nice number.
no, all over, let's say I had 6n to the 5th minus 2n. That'll do. So this would have been some pattern that I recognized when I found my nth term, but I'm not interested in my nth term. I'm interested in what happens when n goes really big. Go big or go home, n. That's what I always say. I don't know. So what is my trick?
0.
No, I have a trick. What's my
No,
trick?
I'm just saying that it's 0.
Oh, is it?
Yes.
What am I doing now? What's my trick?
You're going to divide by the largest degree.
N to the fifths, right? I'm dividing every term by n to the fifths, which is a legal algebraic move. Nothing wrong with that. And it looks like it's making things worse, but I assure you,
Making things better.
things are getting a lot better. Oh, I'm dividing by n to the fifth, not 6n to the fifth.
Remember what the people said.
Let's see. Nope. What am I doing now? Minus 2n over n to the fifth. Here we go. Okay. So let's simplify this. So this is the same as 2 over n plus,
3 over n to the third
yep,
minus 1 over n to the fifth. All over 6 minus
nope.
2 over n.
Okay, so let's actually take these limits. Take it to the limit.
2 over n is 0.
2 over n.
As n approaching infinity is 0.
Do we have a consensus? Do we agree?
Yes.
3 over n cubed. 3 divided by really, really big numbers. I'm dividing
Still
my
0.
my 3 pizzas this time. I'm dividing into infinitely many slices.
Still 0.
Because I have infinitely many friends, and I'm sharing these 3 pizzas with all of them. I still have friends that won't be appreciative of my gift. Well, unless I'm going to live forever, and somehow so is the human race, and I'm going to be friends with every single human from now on. Yeah. Yeah.
That'd make it a lot easier.
And let's see, what is 1 over n to the fifth going to?
0
0. So 0 plus 0 minus 0
equals 0.
is going to be 0. I have a
I'm
hunch.
pretty sure that was on SNL. 0 plus 0 minus 0 equals 0.
I didn't know this one. What is the limit as n approaches infinity of 6?
6.
It's just always 6. Good old 6. Forever. It will always be 6. And 2 over n to the fourth? 0. So what does this simplify to become? This is 0
6
over 6,
equals 0.
which is 0. And now since this limit exists, that means I could actually find an infinite sum, or a sum of the infinite list of terms composed by this pattern. The sum itself wasn't infinite. The sum was
Would that involve finding that sum involve E?
E would be derived by some of these limits. Some of the patterns and definitions of E derived E originally by taking limits as values would go off to infinity.
We
Yeah.
have to add 1 over n minus 1
Yeah.
minus 1.
Yeah, and you'd have to just do as n approaches infinity. Yeah. But anyways, so that's the general idea tonight. So what you're going to be doing is finding limits. Any number divided by infinity, or a number that goes to infinity, is going to be 0.
What do we do with these?
Hold on to them. Use them for review later. So that'll do. So there we go.